So, hello everyone. My name is Tilok Shadukhan and I'm from Kolkata, West Bengal. And I have done my BSc and MSc both in physics from West Bengal State University and CSJMU Kanpur. And apart from that, I have done various internships, some of them like Introduction to Data Science at IIT BHU Technics. And recently, I am working on a project in Triple IT Hyderabad on large celestial objects. So that was quite a brief introduction about me, and so I'll be teaching you physics, specifically the JEE and NEET physics. Uh, so first of all, I'll just put you in the next slide, which is the outline or the titles of the chapters that is our in the syllabus in JEE physics. So I'll just head over to the next slide, which is there is it, and as you can see here, there is 1 2 3 4 5 and 1 2 3 4 20 chapters uh, in this uh, in this slide. The titles are 20. So and we have around 100 hours, right? So this is our 100-hour planning. So 100 hours of planning, and so as we can see, there is 20 chapters, so we can devote around 5 hours on an average, 5 hours on each chapter, uh, as there is 100 hours and there is 20 chapters. So we will be giving on an average 5 hours in each single chapter. Now, uh, now there are chapters which will does not take long amount of time. For an example, physics and measurement. This chapter does not take 5 hours. This will take maximum like 1 or 2 hours, and consequently laws of motion, this will take a long at least 4 to 5 hours. This will take 4 to 5 hours. Rotational motion, this will also take 3 to 4 hours. So as you can see that I have assumed the average 5 hours. So average 5 hours, right? So it will not take 5 hours each and every single chapter. For an example, electrostatics, this chapter will take long. For an example, this will take 6 to 7 hours. And electromagnetic waves, this will also take 6 to 7 hours, and so on, right? So that is why I have just said that I will, or we can devote around 5 hours on an average in each and every single chapter, in our this 100-hour study planning, right? So so that is just simply our 100-hour study planning. And the thing is, i'll just I'll just make a concept. I'll just discuss a concept right now about on the topic of electrostatics in the chapter. Sorry, I'll just discuss about a chapter, about a topic which is the Gauss's law, and which is from the chapter electrostatics, right? So I'll just discuss about the Gauss's law, right? So let's GAU Gauss's. Now, to understand what is Gauss's law, and its importance and why it is important in electrostatics, first of all, we have to understand what is significance of Gauss's law. And to understand that, we need to go through a little bit of introduction about electrostatics and charge and electric field and all of the stuff. So for an example, I have a charge that is Q, right? So I'm just saying that I have a charge Q. So if this is a charged particle, there will be a electric field around this charged particle. So what will be the electric field around the charged particle? From the Coulomb's law, we know the electric field around any single charged particle is going to be very simple. That is my E, which is going to be 1 divided by 4 pi epsilon naught Q divided by R square times R cap. So this will be our electric field near the charged particle, right? So this will be our electric field near the charged particle. And And in the integral form, and for an example, if this is not a single charged particle and it is for an example, it is a line charge, right? So if this is a line charge, that means it has a line charge density, so which is lambda. We are assuming which is lambda. So if this is a lambda, this is, and I am assuming this is dl, which is the infinitesimal length in this particular line line charge, and where, so the charge which will be in this particular region is going to be lambda times dl, right? Now if I ask you a simple question, which is what will be the electric field due to this particular region in this in a nearest point, for an example this point. So I'm assuming this point and I'm naming this point as a P point. So I'm asking you what will be the electric field at this particular point at P. So it's very simple, as we can say that DE, the electric field, is going to be very simple, and it is going to be 1 divided by 4 pi epsilon naught dq divided by my r square times r cap, right? That is simple. My electric field, according to the Coulomb's law, it will come around this, like this. So I'll just replace the dq with the integration, and if I just calculate the total electric field from this integration, from this infinitesimal electric field to total electric field, I just need to perform uh, a particular integration, which is 1 divided by 4 pi epsilon naught integral lambda dl divided by r square times r cap. So this is my total electric field in the nearest point from the distance this due to this dl region into the nearest distance, which is my p, right? So that is the thing, and the thing is, this is my electric field, this will be my electric field, right, for this total where, if I say this is a point and this is b and this, so this is ab where has an electric field, total ab where has an electric field at the p point, right, is simply this, right? So now imagine if this integral becomes very complicated. It becomes, as you can see, it becomes, the more you see, the more you will think about, and the more you will realize that how complicated this integral can become. And it will be a really hectic process to calculate and compute this integral. So to avoid complications and to avoid a lot of gigantic terms, mathematical terms, we have introduced the Gauss's law. Now what is the Gauss's law? So I'll just simply write down the, first of all, I'll just simply write down the mathematical form of the Gauss's law. What is the mathematical form of the Gauss's law? So I'll just put an integral sign. This is a surface integral, by the way. Don't get scared about this symbol. It's not that difficult. So which is E, this is my E dot dA, and this is going to be 1 divided by epsilon naught q ENC. So this is just the simple equation. This is just a simple form of equation of Gauss's law, which is E dot dA, which is equals to 1 by epsilon naught q enclose. Now q enclose is the total surface, the closed surface, and sorry, q enclose is the charge enclosed by the surface. That's simple. So what is the physical interpretation of this particular equation? Now we are going to understand about that right now. So the physical interpretation of this idea is very simple. So if we have a particular charge, this, right, so we are going to assume there is a surface around it, right? And what is the surface area? So if this is a charge in three-dimensional space, what will be the surface area? The surface area will be 4 pi r square. right? The surface area is going to be 4 pi r square. So my electric field E dot dA for this particular, so this is my surface integral. So for my this particular system, this thing is going to be 1 divided by epsilon naught q enclosed. This is my q plus enclosed charge q, so q. So which will be q divided by epsilon naught. So this is my the thing that we are speaking, which is E dot dA, and in the surface area, this is the Gauss's law. And we are going to have a various interpretation of the Gauss's law at the same time. We are going to understand what are the pros and the cons of using the Gauss's law and having um, various things of why we should avoid this cumbersome integrals and Coulomb's law to and incorporate Gauss's law to have a better understanding about the electrostatics. And we're going to get through in all of those things in our preceding sections. So that was a brief video about me and how and the topic that I just discussed, which is Gauss's law. And yeah, that's it.